All right, good evening, guys. Let's start with our presentation today. So, before I start, let me just introduce myself. My name is Ugenteraan. You guys can call me Ugain if you like to address me. I'm currently working as a senior AI engineer in DG, and so today I'm going to be talking about this implementing multi-layer perceptron with PyTorch. So for those who doesn't know what multi-layer perceptron, it's a type of neural network. It's the first type of neural network, so to say. So it's a good thing if you guys can master this before you can go into any kind of deep learning algorithms. All right, so let me just give you an overview of what are we going to be learning today or rather what I'm going to be teaching you guys today, and so that you can adjust your expectations and you will know what kind of question to ask later. All right, so I've thought about teaching to I've thought about the level of teaching that I'm going to be doing today. So basically, there are multiple levels that you can learn when it comes to neural network. One is through the mathematics, which is basically you will be deriving all those algorithms from scratch and try to implement it without any library. So that's the lowest level that you can go, and it's actually quite good if you can do that, so that you will be able to read all kinds of research paper and try to implement your own solution, right? And there's also this another part whereby you don't understand what is neural network. You just treat it as a black box, and you just use all this library like PyTorch, TensorFlow, and try to implement it just using some basic intuition, which is not to say that it's a bad thing to do. It all depends on your use case and your goal. If you aspire to become a researcher, then obviously the second method is not for you. You should be doing the first method. And if you aspire to be someone who just come and do the work and go back home, then yeah, of course the second method will be just suitable for you. So what I'm going to be teaching you today instead is to give you a little bit of intuition on how the neural network works. Not too much mathematics, but I'm not going to be going through this entire thing without any mathematics as well. So maths is something that's vital for this entire presentation. So you're going to be learning a bit of the intuition behind neural networks. Not too much of those intuition, because neural networks has many different parts of it. So you're just going to learn the first part of it, of the intuition. And using this intuition, we're going to implement this neural network with PyTorch. At first, I wanted to teach you guys how to implement using just NumPy, but that would require a lot of mathematics, and I don't think we can cover the entire thing just tonight. So that's why I'm going with this. So uh, let's not call this a lecture. Let's just call it a simple two-way conversation. So although I'm going to be using slides and all, I expect you guys to just chime in and ask questions and make it an interesting conversation so that we can learn from each other. Even though I've been doing all this neural network for many years, there will be some parts that I might not know as well, or something that I might not have thought about as well, right? So I get to learn from the questions as well. So it's really beneficial for both sides. So I'll be stopping whatever that I'm talking for every few slides to open the floor for questions, so you guys can have the opportunity to ask any kind of questions that I talked about. If there's no question, I'm just gonna assume that everybody understands whatever that I'm talking about and just move on from there. So that's gonna be the lecture class today. So far, do you guys have any questions before we start? All right, no questions. So let's start. Okay, so before I go into any kind of mathematics or whatever fancy words with the biological neurons, the brains, and whatever, let's talk about a simple scenario and a decision-making neuron, right? So I'm pretty sure you guys have seen some sort of notes or lecture or whatever about neural networks, and you might have come across weights, biases, those kind of things, and it might have been a mystery to you what they all were doing in neural network, right? So I'm just gonna try and give you intuition on what are these weights and biases are. So let's start with this scenario. Let's say there's a carnival happening in your city, right? Some fun fair or whatever, and you really want to go for this carnival, but there are three factors that will influence your decision whether or not you should go to the carnival, right? So let's say the first factor is the weather. I mean, obviously we don't want to go there if it's raining heavily, right? I mean, who wants to go to a carnival when it's raining heavily? It's just no point to go there. So that's the first factor. So whether or not it's a nice weather that day will be the first factor. So 0 for false, 1 for true, right? So remember that. The second one is, obviously a lot of people would prefer to go with their friends or family. It's much more fun that way. So that's going to be your second factor, right? So whether or not they come. So 1 and 0 again. And let's say the third one is the public transport. Let's say you don't have a car or you don't have a motorbike and you rely on public transport. So that's gonna be your third factor. If there's a public transport, it's 1. If there's no public transport, it's 0. So now let's try a simple mental exercise. Let's try to assign importance to each one of these factor, right? These importance are also known as weights in neural network terms. Okay, so the first factor, I mean, obviously the weather would be the highest importance in these three criterias that we have. So let's put some high number for that weather. And let's say the second one is not that much of an importance to you, right? Let's say that your friend is, whether or not your friend is coming, maybe you give it a 2 or 3, right? And the third one is the public transport is maybe something important for you because this carnival is quite far away. So it's kind of tiring to walk, right? So let's put that as the second influencer here, right? So now let's say based on these weights or based on this importance that we have selected, we need some sort of a decision maker, some sort of programming. I mean, of course, we can do this using a traditional rule-based programming, but let's try to use a single neuron for this, right? So before that, let's look back at our weight assignation again. So let's limit the weight assignation to from 1 to 10. So the first factor, like I said, it's obviously the most important one, so we put it as 8. And the second factor, whether or not your friend is coming, is not that much of an influence, so we put it as 3. And then the third one, the public transport, like I said, is the second major influencing, right? So we put it as 6. So this is going to be your neuron, okay? So this neuron is just an imaginary circle, so you don't have to try and kind of imagine any kind of a solid object with that. So let's just imagine a single neuron looks like this, right? So this neuron has 3 connections to it, and each of these 3 connections has a weight assigned to it. So the first one is 8, second one is 3, third one is 6. These weights are the one that we talked about earlier, 8, 3, and 6. Okay, so imagine this neural network can do some sort of processing using these weights and the input that you give, and there will be an output comes out at the end. Okay, so that's the purpose of this neuron, to make decision based on the weight and based on the input that you give, right? So now let's simulate this input. So let's say that the weather is nice, so that's 1. And let's say your friend is not coming, so that's 0. And let's say there's no public transport available, so again 0. So let's multiply each one of these input to the weight that we just assigned and see what's the result. So we get 1 times 8 plus 0 times 3 plus 0 times 6. So that gives us 8, right? Because 8 plus 0 plus 0. So 8 is the total value that we get. Now, in order to simulate some kind of decision-making skill to this neuron, we need something called activation function. You can imagine this activation function as a kind of like a gate that outputs 1 whenever some sort of criteria is met, and the output is 0 whenever the criteria is not met. Okay, so that's going to be our activation function. So there's a name for this activation function. It's called threshold function. So this is the most basic activation function that you guys should know about. There are a lot of other activation functions as well, ReLU, sigmoid, tonnage, and so on, but this is the most basic one. It's we don't normally use this in today's neural network context, but it's something that's easy to learn and something that you should know about. So let's set our threshold function to 10. If all those result that we got just now is more than 10, then the output is 1, or it's going to be 0. Simple enough, right? So let's see how that works for our neural network. So since earlier we got 8 and we apply the activation function, it is less than 10, right? So it's going to be 0. So that's the output of it. So you see how this decision making worked since just now. So since we only have one of the input as 1, which is the weather, so this decision making neuron decided that we are not going to the carnival, right? So now this is just one example of it. What do you think would happen if we change the inputs a bit, right? I mean, let's say that the second one is 1, right? So if the second one is 1, so we would have gotten 8 plus 3 plus 0. So that means we would have gotten 11. And 11 is more than 10. So we would have gotten 1. So that means when the weather was nice and when your friend is coming, even though the public transport was not available, you would be still going for the carnival. So that's how the decision making is simulated in this neuron, in a single perceptron or a neuron, right? Same goes. If you were to change your threshold function, let's say that you think this is too extreme, you think that it should be reduced, you can always reduce the threshold function. You can, instead of 10, you can put 8, 9, 7, or whatever that suits you. Now, the more changes you make for this threshold function, the more you can modify an output to your liking. All right. So now you may ask, what's the purpose of all this thing, right, in this neuron? Now, bear in mind, I'm just trying to give you an intuition of how a single neuron works. This example by itself doesn't mean anything. It's just a lousy example that that's simple enough to give you an explanation on how the weights and the activation function works in a single neuron, right? So again, if you change these inputs to whatever that you need, I mean to whatever that you have on that day. For example, if it's not if it's raining instead, then it's going to be 0. And then even if your friends is coming, let's say it's 3, and let's say that there's public transport available, 1. So 0, 1, 1. That would give you 3 plus 6, 9, which still doesn't match the threshold function, and it's going to give you 0. So that's how it simulates the real life decision making skills over here, right? So this is the one example of it. All right. So now that you know, or now that you have some sort of intuition of how one simple neuron works, imagine what tens of neurons that are connected to each other can do. All right. So this is what's been happening to all the neural networks. So each one of these neurons are decision makers. So they make some sort of decision based on the input that we have given. The input could be anything. It could be an image with pixel values as the input, or it could be just simply be zeros and one, binary inputs, or some sort of housing price for you to predict something later on, or some sort of age, or a stock market, or anything at all. So as long as the inputs are numbers, it can still accept it, do some sort of calculation with the weight, and give you the output that you require. How does it do all that? We'll get there later in a bit. But so far, do you guys have any questions? All right, so I'm just gonna assume that everybody understands. Okay, cool. So if you guys have any question, just feel free to stop me and just ask me a question, or you can even put in the chat there, and we can discuss on what you don't understand, right? All right, so that's how this neural network is connected. So just to add on a little bit more to what we just talked about, the activation function is not gonna be something that's so primitive, just like how we talked about earlier with the threshold function. So here we will be using more advanced activation function, like I said, tan, relu, sigmoid, and so on. The reason why we are using more advanced activation function is because the threshold function is just merely giving 0 and 1, right? It's not enough to capture better informations for real life purposes. For example, if you want to predict housing prices, right? What's the point of getting 0 and 1? It's not a binary kind of classification, right? So that's why we need probably sigmoid or tanh, where they can squash the inputs to 0 in between 0 to 1, so it can give you any kind of float information there. So each one of this float information represents um, a different feature than the threshold function that would give you, right? All right, so now we're going to talk about optimization. So earlier we talked about all these weights, biases, and threshold function, right? Now the question is, where do the weights come from? So earlier, for this one single neuron, the weights were very easy to pick. I mean, we only had three scenarios, right? I mean, three factors, right, to pick the three weights. So we could just even do some trial and error until we get the desired output that we want. That's why I say that this is a lousy example, because it's very simple. There's like no point to use any kind of neuron in this first place for this use case. You could have just used a rule-based programming to achieve this use case. But again, like I said, it was just to give you an intuition. Now that you have known about this would make even more sense. Now here, since so many neurons are connected to each other, you're gonna have like thousands of weights here. Each one will be different than the other. So how are you going to determine the weights in each one of these connection to get the output that you desire? So that's where this optimization comes from. All right, so obviously we can't do that by hand. I mean, one by one trial and error is out of the question. So we come to the optimization over here. So the goal of optimization is to find the weights to the weight values inside the neural network to for the given input and output. All right. So now the question is, how does this optimization works? So you guys have probably taken your calculus class, right? And in your calculus class we have these derivatives or differentiation, as we call it, right? So we have this differentiation or derivative, whereby this differentiation gives you the slope of the function. So we have a function or an equation. Let's just call it equation, right? Function equation is the same thing. So you have this equation, y equals something something something, y equal x square, y equal x square plus 2, whatever, right? When you calculate the derivative for this y, you're gonna get another equation, and this equation represents the slope of the function. So what do we mean by that? So let's say you have this equation that represents this blue line, right? So you have this x cube plus whatever, and when you plot it in the graph, you get this blue line, right? So now that you have this blue line, when you differentiate that y equal whatever, that x square blah whatever equation, you will get this red line instead. All right, so this red line is what we call as the tangent line or the slope, right? Slope as in the you can also call it gradient. Okay, so what that means is, as you can see in this particular red point over here, the slope is this way. So that means the slope is increasing upwards, right? And over here at the top, you're gonna get a slope of 0, because it's you reach the top of the function. So there's no going to the right or going to the left, it's 0. As you go to the front, it's gonna become negative, the slope, because you're descending, right? So it's gonna become negative and negative all the way until you go up again or you stay static again. So if you notice, there are like few places where the slope can be 0, either at this peak or at this peak over here. So in both of these peak, there's not going to be a gradient, because you are at your at a point where there's no movement occurs to the left or right. So it's just going to stay neutral. So these are the three things that you should know when we talk about gradients. So it's either positive gradient, negative gradient, or 0 gradient. All right, so 0 gradient is where the function is at its peak. Okay, so what's the use of this derivative? So that's the question, right? So let's just see a simple example. You can ignore all this mathematics at the right side. Now there's just one more thing before optimization that we need to talk about that pertains to neural network as well. That's the loss function. Okay, so backpropagation is the process of calculating the gradients for each one of these weights, right? So if you remember earlier, when we are doing the calculation for the gradient over here, right? Sorry, see, when we are doing the calculation for the gradient, you would always want to do the derivation with respect to some variable. So in this case, dy over dx, it means that we are differentiating this y with respect to the x value. So the x value is obviously this one and the y value is this one. So what that means is we are trying to find the rate of change. When you do that derivation, you get how much of x is how much of y would be changed if the x is changed slightly. So that also the slope again. So if it's positive, then the y is going to be bigger and bigger. If it's negative, then the y is going to be lesser and lesser. It makes sense, right? I mean, when the slope is negative, the y value is decreasing right over here, and when the slope is positive, the y value is increasing. When the slope is 0, the y value stays stagnant. So that's how this backpropagation, this derivation, and this function comes together, right? So the same thing here. What we are going to do here is we are going to define a loss function. All right, that's step 1. Now, what is this loss function? To give you an analogy, imagine that you are responsible for teaching standard 2 kids mathematics, right? So what you normally do is before the exam, you give them a lot of exercises, right? So you give them a lot of exercises, you give them the answers to the exercises as well, right? So the reason why you're doing this is so that they can try and do those questions themselves, and then they can look at the answer. If the answer is correct, then it gives them a positive reward to themselves. If the answer is wrong, they correct their mistakes, and the next time they will do better, hopefully, right? So that's kind of like a loss function here as well. So when we give it the input to the neural network, it gives you some kind of output based on whatever weight that it have, right? Now we need to check whether this output is correct or not. So that's why we normally have the correct labels with us as well. All right, so this loss function, what it does is it compares these two things. So the output from the neural network is compared with the real output that it should have been, right? So you don't have to go deep with these mathematical equations yet. All you need to know is that this is the real value, this is the prediction value, and we are comparing them. You don't have to worry about all these other things, right? So the square is just there to make it a nice function that has curves, right? So you have this loss function. Now, so far, do you guys have any questions? All right, so now that we have this loss function, our goal is to try and reduce the loss as much as possible, right? I mean, it's only natural. Like the analogy earlier, you want to reduce the mistakes that you make such that your answers and the real actual answers are same to each other, right? So think about the analogy again. If the real answer and your answer is different, then there's going to be a lot of loss, right? If the real answer and your answers are similar, then there's going to be very less loss or zero loss. Okay, so the same thing here. If the loss is high, that means our neural network is not doing good. All the predictions are very far away from the target that we want to predict. If the loss is low, then that means that the prediction and the target is not very far off, right? So that's why we want to reduce the loss function as much as possible. Now comes back again the backpropagation and the derivation. So now that you have this loss function, right, when you do the derivation on the loss function with respect to sum of the weight, one of the weight, you're gonna get a slope like this. This will be the loss function, and you're gonna get a slope like this. So essentially what you want to do is you want to go down, right? So that the loss function, which is y over here, I think you can use this. So this is the loss function, and this is your parameter. This is your weight parameter, right? So if this is where your current loss function is, what you want to do is find the slope that goes downhill and update the weight based on the slope. So this is what we call as gradient descent. So that's because you are descending the gradient, right? So in the first iteration you might go here, in the second iteration you might go here, third iteration, and so on. And as you train and train the neural network again and again, it finally reached the convergence over here. So this represents the lowest value of loss that is achievable, right? So again, this is the loss function, and this is the parameter, weight parameter, this is this is the graph that shows the loss function against a weight parameter. So this shows that while if we change the weight parameter to some sort of value over here, the loss function is going to be at its lowest. So we're going to do the same thing for each and every weight parameter there is over here. So each and every weight parameter is gonna go through this back propagation to the derivation, and we're gonna find the optimal weight value for each one of these in every iteration. All right, so this is what we call as the training part of the neural network. So during the training, this is what we are doing. We are calculating the loss function, and then we are doing some sort of derivation to the back propagation, so to the loss function, and then we are updating the weights of the value of the weights. All right, so when we do that, when we keep on doing this to certain extent, we're gonna eventually go to a value of loss such that it's super low, right? So that's how we know the neural network is doing good. All right, okay, so far any questions? All right, so earlier we used just a bunch of numbers, right? I mean, it's just scalars. We call it scalars. It's just normal numbers, right? Now in neural network, in here, you can't be using all these scalars anymore. You can't be putting inputs one by one in a list or array just like that. You're gonna need something else, something compact. So that's where vectors come in. So if you Google for vectors, there's going to be a lot of definitions. Something that has direction, something that has magnitude, something that has length, things like that. But we don't, those are physics definition. We want to go with something more mathematical, something more abstract. So in mathematics, there's no one definition for vectors. Vectors are just described using a bunch of rules, and using the rules you can find out whether a thing is a vector or not. All right, so but to give you again, this entire lecture or class is to give you some sort of intuition, right? So the intuition for vector is it's just a bunch of numbers arranged in a one column matrix. So this is just a one column matrix, and the best part about vector is you give meaning to the vector, right? So I mean, even numbers 1 2 3 4 5, right? I mean, it can mean anything. We are the one that gives meaning to the numbers. 2 dogs, 2 cats, 3 cows. We describe everyday objects using numbers, right? I mean, it can also be 3 computers, 3 planes, 3 cars, or whatever. The number is still the same, it's 3, but the objects are different. Now when you attach an object to this, the abstract definition of numbers, the meaning change, right? Same thing with vectors, no difference, right? So don't need to confuse vectors with numbers or whatever. So again, vectors are also just some abstract objects that are out there, and we give meaning to these vectors. So in the context of machine learning, we represent data with vectors. It's easier to do that way because vectors are like a group, right? Instead of describing them one by one, we can just describe it as a group. Okay, so that's how vectors that's how you get an idea about vectors. So now let's see how this vector can be connected to our earlier example. So our earlier example, if you remember, our input was 100, right? And the weight was 836. So this is how you multiply two vectors together. I mean, the weight is not exactly a vector, but you get the point. It's actually a one row matrix, but it's fine. I just want to show you an example over here. So you have this vector 100 and the weight 836, and the way you multiply is the first row is multiplied with the first column plus the second row multiplied with the second column plus the third row multiplied with the third column. So if you remember your matrix multiplication, this is how you multiply matrix, right? Don't go around asking why matrix are multiplied this way. It's just the rule, right? I mean, it's just how it's defined, matrix multiplication. There's also something else called dot product, which is a bit more intuitional. But again, this is how matrix is multiplied. The reason why they put it this way is so that it's because a lot of applications can be developed through this way of operation. All right, so now you see all this 1 times 8 plus 0 times 3 plus 0 times 6 equal to 8. It's the same thing as how we got previously, except that this time we are multiplying it using vectors and matrices instead of just multiplying it one by one and then connecting them just like that, right? So this is how a vector is used. Now comes the time to try and implement our solutions. All right, how many of you guys here know about MNIST dataset? All right, I'll take it as no one here knows about MNIST dataset. Okay, MNIST dataset is just some handwritten digits like this, or like this actually. Alright, I'm just going to show you the image. Okay, so MNIST dataset is just the and handwritten digits that we are trying to train our neural network on, right? So this is some example of it. So you can see that even though these three numbers are the same, 2 2 2, it's written differently, right? So it's obvious that you can't implement some sort of solution or decision maker using some rule-based traditional programming, right? I mean, how are you going to implement the rules to decide this is 2, this is 3? You can't. So what you do instead is implement a neural network like this and let the neural network learn the weights so that it can output us the value that we want. So it outputs between 0 to 9, right? I mean, so if the neuron at the 0th index is the highest value, that means the given input is 0. If the neuron at the 5th index is the highest value, then the given input is 4, and so on. So that's how we so that's how this MNIST dataset is. So we're gonna try and implement the MNIST dataset here. Alright, so you guys can follow along with this tutorial if you want to. I'm just gonna try and copy paste some of it from my previous solution already, but if you guys need me to slow down, just do let me know. Alright, let's see. This is my previous implementation which I'm gonna be using. Alright, so the imports are not really that important, so I'm just gonna copy and paste it here instead of just typing it one by one. So to explain to you guys, this is the PyTorch libraries. All the three of these, actually 4 of these, are all PyTorch library. The first one is the bare library. The second one is the neural network module in the torch itself. The third one is just some it's needed for some function, like I said, the activation function, loss function. So those kind of things can be taken from the third one, and this is just purely for the data set alone. All right. All right, so normally when it comes to vectors and matrices in Python, we when we want to do any kind of operation with matrices, like I said, the matrix multiplication or whatever, we're gonna need this numpy, right? So this matplotlib is there just for us to plot the images and see for ourselves how do they work. So that's these are the libraries that we're going to be using, right? Okay, so I'm just gonna copy this again and I'll tell you guys one by one what these are. All right, so instead of just downloading the MNIST dataset from website and putting it here and loading it, that's just gonna be tedious. So that's why we use this Torch Vision datasets module over here. So PyTorch already did us a favor by adding the MNIST dataset into their libraries itself. So that's how we can just simply call MNIST over here and then download the things for ourselves. Now this is going to be train dataset and validation dataset. Okay, I'll give you an intuition of what is a train dataset and a validation dataset. Remember our analogy earlier where you're the teacher and you are teaching some students or some 8-year-old kids mathematics, right? Now you're going to train them with a lot of practice questions, but you're never going to show them the exam questions, right? So you want it to be fair. The exam questions are never seen by any of the students at all. You let them practice and then you give the exam questions at the end to really evaluate them, right? I mean, that's how we know if the people are cheating or if the students are really good at what they do or they are just merely memorizing some example, right? I mean, you can give a lot of practice to certain student and they wouldn't understand anything, but they would just memorize all this formula or the question and answers and try to replicate that in the exam, right? So that's why you don't want to give the exam solution or even the exam questions to them, right? So similar to that, this is what's happening here. So we have train dataset. Train dataset is what we are going to be using to train the neural network. So remember all those input, output, loss function, derivative. So that's going to be going on with the train dataset. After the training is finished, after the neural network has a very high accuracy or a very low loss in the training dataset, then we're going to bring in the validation dataset and really test them this time. Validation dataset is something that the neural network have never seen. So if it performs well on validation dataset, we can be confident that the neural network will be deployable in real life. Okay, so that's how the trained dataset and validation dataset plays their role. Again, same thing as the students earlier. Okay, don't worry about this loader as much. PyTorch make use of this data loader wrapper so that we can do some additional configurations to it. For example, like the shuffling, or if you want to transform the dataset or the batch size. A batch size is just basically in a single iteration how many images that you want to put at one shot. I mean, you can't be putting one by one images to the neural network. It's just gonna take forever. So you make use of this batch to give it one shot. So this is how matrix and vectors works. All right, because if you just use constants, the numbers, scalars, you're not gonna be able to put in batch. But if you use matrix and vectors, you will be able to put in as batch. All right, so this is what the four codes here work. So our batch size is 32. It's just an arbitrary number. It can even be 24 or 10, so it doesn't really matter. So we'll just keep it as 32 here. All right, so before we start with any kind of implementation, let's just see for ourselves how the how this thing looks like. Okay, so like I said, we're gonna need the train loader to get the data, right? So we are using the train loader here. So we're gonna see some data from the training data set. Each of this training data set has two variables. One is the image itself, and second is the labels. By label, what I mean is basically the real answer, right? So here we just see the size of it. This is not really that important for us. What we really need is this one. All right, so you can see here I'm just plotting 10 of these images, so not much. You can just ignore these things. Now here is where these two things all right, so these two things are the most important one over here. So what I'm doing here is I am displaying the x, which is this one, the x variable, which is the images, and reshaping them to 28 because all of these images, their size is 28 by 28, 28 height, 28 width, right? Don't worry about this as well. So the reshaping is necessary because in the data set here, all of these images, right, they are smashed into a single long vector. So 28 times 28 is 784, so it's just a one long 784 sized vector, right? So that's why I'm reshaping here so that we can see the image. And just to give you guys a refresher, all images are represented through pixels. Okay, so each one of those the element in the vectors represent the pixels. So the first ever element in the vector represent the pixel value at the 0th position, second one at the first position, third one at the second position, and so on, all the way up until the end. So that's how the images are represented as vectors or matrices. Okay, so the second one is I'm going to name each one of these as Y train as their label itself. Okay, so Y train is this, like I said, it's label, right? So this is what the label gonna be. So let's plot it and see. All right, there you go. So this is class 4, class 3, class 6, and so on, class 6. So this is our training data set, just 10 of it, right? Not all of it. Let's try again. See, this time it's different. Now the reason why it differs is because we have the shuffle through over here. If we were to put the shuffle as 4, then it's just going to be the same thing over and over again. So that's how the data loader is helping us out, right? So generally when we are training neural networks, we shuffle things so that in every iteration we get a different inputs. Okay, so this is so far that we have come. Now let's go and implement our neural network over here. So just gonna be explaining to you guys over here. All right, so far before we continue, do you guys have any questions? All right, no questions. Okay, so when you are implementing a neural network using PyTorch, certain things are a must. Okay, so the first must is this: you need to inherit the module part from this neural network library, right? So NN module. The reason why is so that you can use all these the abstract functions over here. So you need to implement this forward function and this init, right? When you implement when you inherit this NN module, these are more towards the programming part of it, so it's not exactly neural networks part of it. So you guys, I'm pretty sure you guys probably can learn this by yourself very fast. All right, so this is also something that's a must. So when you are implementing the neural network class, you need to call the super constructor, the parent, so that of this NN module, so that you kind of give it an a hint that you are implementing a neural network module over here. All right, so we're going to be implementing 3 layers of neural network. All right, not as much as 5 or 6 layers. All right, now you have to define the input and the output, and also whatever that's in between. Okay, so the first one is it takes a long vector, right? The vector size is 28 times 28, which is 784. You can just put it this way as well, it's not a big deal, right? And these vectors are going to be connected to 50 neurons. Okay, so that's why the second neural network layer, the second layer, have to start from 50, because the previous one is 50, right? Now the 50 goes to another 50. Now this is also an arbitrary number, so the 50 can even go to 34, it doesn't really matter. but you need to make sure that in the third layer you change this also to 34. All right, so I'm just probably going to keep it to 40. So these are just some hyperparameters. All right, you can change to whatever number you want, and you can see how that affects the result later on. All right, so here we're just gonna go with 40, and of course the last layer should be 10. This is the output layer. Now the reason why the output layer is 10 is because our prediction goes from 0 to 9. All right, we can't put this to a higher number or a lower number because we're gonna use this to calculate the loss function earlier. Remember, we had the loss function, right? So our y over here is also a size 10. So you can't really put this to a different size, or else there's gonna be an error, right? The vectors doesn't match when you calculate the loss. All right, so that's just the initialization part of it. Now this is where the real neural network calculation happens. All right, so the first thing that we are going to be doing is we are taking the input x and we are reshaping it to this is the batch number. So -1 doesn't really mean anything. Like I said, we are going to put into the batches, right? 32. So this is going to be the batch number, and we are reshaping it to 28 times 28, which is 784. And then the second one is, once that's done, we're gonna use the FC1, which is the first neural network, and use this input to it inside it. Once we have used it, then we're gonna apply the ReLU activation function. So like I said, there's activation functions here, and we are using ReLU. So we use ReLU activation function once the input is calculated, and that's your X. Again, now you put it inside the FC2 instead, now the second layer. So you put inside there, and again you use the ReLU activation function. All right, and then comes the third part. You use the this output to the third neural network layer, and this time you apply something called softmax. All right, softmax is another activation function that has a special property. What softmax do is it when you give a bunch of input, it's going to squash all of them between 0 to 1. That means when you sum all of this output, you get 1. Okay, so the reason why we do this is because at the end output layer, we only want one of those neuron to have the highest value, while the others to have a lower value, right? So when you apply a softmax activation function, you're gonna get only one neuron with a high value, and then the rest with maybe diminishing values. So this also represents probability. All right, so I mean, if you remember, your probability should always be between 0 to 1, inclusive of 0 to 1. So when you have 10 things and you want the probability of which one you want to pick, obviously you want all of them to be between 0 to 1, and the second criteria is when all of them are summed together, they equal to 1. All right, so that's how the softmax kind of imitate the probabilistic scenario over here. All right, okay, so that's your neural network. So now let's try to define our loss functions and optimizer. Okay, so this is the model, MLP. So I'm just calling the MLP model over here. Now we have the optimizer. So we talked about backpropagation derivatives, right? So SGD means stochastic gradient descent. So we have already talked about gradient descent earlier over here. So gradient descent is just basically starting from some sort of point, and it just goes down and down until we find the best value for the weight parameter, so that the loss function is low. So that's what this is going to do for us. So that's learning rate. So learning rate means it controls how much it goes down the hill. All right, so to give you an example, let's say you are at the top of the hill and you want to go to the bottom of the hill, right? So you want to adjust your steps. You don't want to go too fast, and you don't want to go too slow, right? I mean, if you go too fast, imagine that you can't change your step, right? You can only always have the constant step. Now if you have a very large step, you're gonna miss the bottom, When it comes to the bottom, you're just going to take another large step and then just go up again, right? I mean, you're not going to get to the bottom, right? So that's why you want to have a slightly smaller step, but then you don't want to have a too small of a step as well, or else you're never going to reach the bottom. So you're just going to have somewhere in between, in the middle. So you're going to have to do some trial and error to find the best learning rate. But normally we would go with 0.01, 0.001, and so on. The larger the model, the lower the learning rate is normally. That's the rule of thumb. Don't worry about momentum. Momentum is just it's a different concept altogether, so don't worry too much about it. And this is your loss function. So I'm just gonna rename this to loss function so that it's easier. All right, cross entropy loss is another loss function in contrast to what we discussed earlier. So this one is known as mean squared error. So it's very straightforward. You get the target, you have the real value, you minus with the prediction, and then you square it, you average it. That's it. This one is a bit different, cross entropy, but it's much more useful for classification task. So you don't really have to know what it does, just know that it's also a sort of a loss function. Okay, so now when I print the model out, this is what I get. So the model consists of 3 layers. The first layer takes the input and then give it to the next 50 neurons, and then the next 50 neuron give it to the next 40 neurons, and then the next 40 neuron produces this 10 final output neurons, right? All right, so now let's go to the training part. Okay, all right, so this is just a training function. All right, remember that function can mean different things. In programming, a function is just a piece of code that we write, but in mathematics, function is a different thing. All right, so you don't want to confuse both of them. Just know the context of what I'm talking about over here. Right, so this is our programming function of training. So it gives the epoch and log interval. Don't really need to mind this part. Okay, before we do anything to the model, right, we need to set the model to certain modes. So we have 2 modes, eval mode and train mode. So during the train mode, all those gradients are ready to be changed, to be trained rather, right? In eval mode, then those weights will be static. We're not going to change the weights anymore. So this is pretty important for you to know in PyTorch. All right, so now let's iterate through our train loader. So like I said earlier, in our train loader, we have 2 variables, data and target. Target is our labels. All right, so first, before anything, you want to refresh the optimizer. So this optimizer over here, right? So you want to clear out whatever calculation that the optimizer has previously. Okay, now let's give the data to the model and then get the output. All right, so now once we got the output from the model, we are going to use the loss function earlier to calculate the loss. All right, so you give the output from the model and the target, the actual target, right? So this both of these are going to be compared, and we're going to have a loss function over here. Now backward is where the back propagation happens. Remember the derivation earlier? So that's where we calculate the loss functions derivation over here, the derivative. So once we have the derivative, we update the weight using the optimizer over here. So there's the gradient descent will work its way down the hill so that we can find the best weights over here. Don't worry about this too much. It's just there to update us about the loss function. All right, so once we have the training function, now we're gonna have the validate function or a testing function, whatever that you want to call. It's the same thing as previous, but this time the model is set to eval mode before we do anything, and it's the same thing. The output from the model is collected, and then we have this loss function over here. This time we are collecting we are just collecting all the loss function over here so that we can see the graph later. All right, and this time we are calculating the accuracy of it as well. So that's why we have this prediction EQ over here. So this is the prediction. So the prediction is basically what we're going to do is we take the output from the model and we get the maximum value from the prediction. Now the maximum value, like I told earlier, is the neuron with the highest output. So that position of the neuron is gonna represent the number that we are looking at, the input. Alright, so that's what's going on over here. So don't worry about this too much. These are just some normal calculations for the loss and accuracy, and again this is just something to print out for us to see the result. Okay, so let's start both of our training and validation. So we're gonna make it for 10 epoch. So this is just a variable to catch all the loss and the accuracies, so that we know whether the model is actually learning or not. Alright, let's go. So this is epoch 1, and in epoch 1 we have the loss for 2.3. Alright, so we are still in epoch 1, but this time the data that we are using is more than 6,000, more than what we had earlier. So as you can see, the loss is decreasing. So this is how it's supposed to be. Sometimes the loss will be increasing slightly. It's nothing to be alarmed of. It's totally normal in neural network. So as you can see here, 3.8 and then suddenly 0.44 again. That's because it's using a different set of images than previously, right? So it's still in the first epoch, so we will be able to see in the second epoch. And in the validation set, we get the loss of 0.32 and the accuracy is 91%, which is not really that bad after all for the first iteration. Okay, so now the second epoch goes on. So you see, earlier during the first epoch, it started out with 2.3, and here now it started off with 0.4, and it's decreasing even further, 0.1, 0.3, and so on. So this is what we have, what we are expecting of our neural network. So let's just wait until it finishes, and while we wait, let's do this. Alright, so we're going to be using the loss V and accuracy V over here to try and plot some graph, so that we can see from epoch 1 to epoch 10 how the loss and the accuracy were changing, right? So you don't have to worry about all this plot stuff. I'm pretty sure you can just Google and learn about them. For now, just think of them as some library that we are using to plot all these numbers, okay? Alright, while it's training, do you guys have any question that you want to ask me? Alright, I'll take it as everybody understands what's going on so far. Okay, so it's very obvious to see over here in our validation set. During the first epoch, we get a loss of 0.3 and an accuracy of 91%. And in the second iteration, you can see it's 92%, 93%, 95%, and the loss has also been decreasing steadily, right? So this is what we are looking for when we are training a neural network: loss and the accuracy. And you sometimes you might have other metrics like precision, recall, and so on as well. but these two are the most common one. So if the generally the loss wants to be you need to decrease the loss while the accuracy has to be increased, right? So that's what's going on here, and it's a very good sign so far. So we just have to wait until 2 more epochs and we're done. We can start from 1, right? So we can even set this epoch to whatever we want. Now when training a neural network, you might think that, okay, if we increase the epochs to 100 or 200 or whatever, it's just going to give us 100% accuracy, right? Now there's some dangerous side to that as well. When you train your neural network too much, you're going to end up overfitting the neural network, which means that the neural like earlier during our example, right, with the standard 2 kids, imagine you gave them too much of practice, right? When you give them too much of practices, they are going to memorize all of these examples at one point, or they're just gonna not generalize. They won't go for understanding, they instead will go for memorization. And then when you give them an exam, they're just gonna do whatever that they have memorized, and they might not be able to extrapolate from their experience to give you a genuine answer, or to give you an original solution to a problem. So that's the same things that's going to happen to a neural network. When you give them too much training data, what they're going to do is just memorize all those things, overfit them themselves, and when you deploy them in real life, they're not going to perform as well. So that's why increasing the epochs is not always a good solution to go. Alright, so we are done with our training. So our final accuracy is 97%, which is not really bad. I mean, compared to the 91% from we had in the first epoch, right? So now let's see the loss and accuracy. So the loss started from 0. I think 2 point something earlier, and it over the 10 epoch it went all the way to 0.01, right? Sorry, 0.1, which is somewhere over here. Accuracy started from 91%, and it increased all the way to 97%. So that's what we could see from here. Now let's try and see what really happened to some of our data sets. So what I'm doing here is just I'm going back to the validation loader, take some data and the target over here, and I'm just inserting this data to the model, the trained model. The model is already set to eval mode, so we don't have to worry. So I'm just inputting those data to the model, and then I'm plotting some of the data, 10 of the data, and the output from the model itself, right? So I'm just gonna try and see what were the predictions of the model. The break is here so that it it just stops at one loop. There you go. So you can see these are the model's prediction, not the target. Okay, so let's see if there's anything wrong here. Yeah, there's nothing wrong over here so far. So 7 is predicted as 7, 4 is predicted as 4, and 5 is predicted as 5, and so on. Now let's do a small experiment over here. So I'm just gonna reduce the number of epochs so that we don't waste a lot of time. Here, right? So I'm going to disable the calculation of the gradient, the back propagation and the updating of the weight. So I just disable those two things. Right now I'm just gonna run everything all at once. Now we'll see whether the neural network learns something or not. Okay, so there you go. So-called training is going on. Loss is at 2.27, and the loss didn't decrease at all. Alright, so it's just dangling around 2.2, 2.3, and so on. Right, we'll see. We'll wait and see up until the 5th. See, the accuracy is just 15%. See, there you go. The loss never decreased at all, and the accuracy did not increase at all as well. So it's just gonna stay 15%. And if we are doing everything right, it's gonna stay at this same value throughout the entire training epoch. And even the training epoch, it's gonna be almost the same over here. See, 2.28, 2.29, 2.3, 2.27. So it's gonna be somewhere around the same loss all the time. There you go, 15% loss. There you go. So validation loss never changed, validation accuracy never changed, and this is our prediction. 7 is predicted as 4, 2 is predicted as 0, 1 is predicted as 3. This one is right, maybe by luck, or it's just the 15% accuracy that we had, and the rest of it is also wrong. So you can see how that the derivation and the optimizer plays a big role in this entire training phase of the neural network, right? All right, so that's about it for the entire session. You guys have been a very obedient audience all this while. So you guys have any question? All right, I'll take it as no question over here. So if you guys have any other question that pops up in your mind, you can just just PM me anytime, so it doesn't matter. And if you need the codes for this, just let me know as well. I can put it in the Discord so that you guys can uh, play around with it, and the slides as well, so I can just give to you guys later as well. All right, that's about it for my presentation. Thank you very much for listening, guys. I will see you guys next time. See you guys.